So a lot of the applications of differential equations are in physics. So I'm going to take this video and go over a little bit of physics notation and terminology. If you've taken physics before, this might be a review. If not, then I'll give you everything you need. One quick discussion before we start that. This class is on ordinary differential equations, which are only good for describing situations with one independent variable and one dependent variable. So we're in a fixed number of dimensions. In physics, or at least in mechanics, which is what we're going to be talking about here, you often want to move throughout 2 or 3 dimensional space. That's too many dimensions for us because our independent variable is going to be time. And so you only have one space dimension available in our study of differential equations, at least in this class. So it doesn't really make sense to restrict movement to a horizontal line or anything. So what we end up doing, and this is natural, is our movement is going to be vertical. So falling or something being thrown in the air. And that kind of makes sense to study one-dimensional motion there. To have more dimensions, you would need something called partial differential equations, which are even more difficult, which they come up a little bit in Math 309 and also in further courses if you're interested. All right, so what physics do we need to know? Well, we're going to use y for vertical motion. That will be our one dimension of motion, so we'll call that position. And one thing we might need to do is pick where 0 is. Natural choice might be the ground. It might not always be the choice of 0. Pick a choice that's convenient for the problem. The problem might pick for you too. And then we need to pick sign as well. So almost always up is positive. Up. But there might be a reason to pick up as negative. So be aware of that. Then v of t is our change in position, and we call that velocity. I think of velocity as, if we're in one dimension, we can think of it as speed with direction, speed with a sign. And then a of t is change in velocity, which is the second derivative of position with respect to time, and that is acceleration. We also have momentum. I think of momentum as the amount of movement. Momentum is given by mv. M is mass. So if you think of a small object, not very massive object, moving very slowly, that's a small amount of movement. If you think of a small object moving quickly, that's more movement. But if you think of a very large object moving slowly, you could argue that's the same amount of movement as a small object moving quickly. And then, of course, a large object moving quickly is the most amount of movement you can have. And all of this is to get to force. So force is going to be the change in momentum. And then usually for us, m will be constant, so we can pull that out as a constant. We're not going to have changing mass objects. You could have like pushing a leaky cart, or you could have rolling a snowball. You could be increasing or decreasing mass. We won't have that. So pull that out as constant. You're only taking derivative of velocity, which means you have acceleration. And if you've taken physics before, you may recognize this as Newton's second law, F equals ma. Okay, in our scenario, we're going to be dealing with gravity, since we have vertical motion. So with gravity, the acceleration will be this gravitational constant, which is the force, calculates the acceleration due to being close to the Earth. The Earth is pulling you towards it, usually approximately 9.81 meters per second squared. We can also do 9.8 in some cases, or sometimes we may even approximate it to 10. Okay, and then our force is mass times acceleration. Remember, all of these have a direction, and usually up is positive, so we're actually going to write negative mg. If we keep our g positive, we'll write negative mg. You could have written g as negative and then had just mg. Stylistic preference. Okay, and the other thing that's usually present in vertical motion is drag. That's usually air resistance, sometimes water resistance. You could be in any fluid you want. It can be in molasses. Okay, and that force is given by alpha times v squared. Okay, alpha is some other constant, so it's already dependent on speed, on velocity. In this case, it doesn't matter. We're doing v squared, so you could say speed or velocity. But then the alpha also can depend on velocity. Okay, the reason we write it like this is it's different if we're going slowly or quickly. So we'll separate out these cases, slow and fast. So when we're slow, alpha depends on v in this way. It's gamma over v, some other constant. That's off the screen. Some other constant divided by v. It's inversely proportional. So then our f is going to be gamma over v times v squared. One of the v's will cancel out, so f will be gamma v. And our drag is always going to be in the opposite direction of motion, so the opposite direction of v. So we actually, what we would like is negative gamma v. So we'll go back and put negative signs here. Alpha is going to be inversely proportional to v and also the opposite sign. If we're going fast, alpha is pretty much constant. So then f is going to be just gamma v squared. And then we also need to go in the opposite direction of motion. But here, v squared, it will never be negative. It's either positive or 0. So we're going to have to pick the sign basically towards the end of this calculation. There is a clunky way you can write this. You could write negative gamma v times magnitude of v, or absolute value of v. Same thing in one dimension. Here, we do now guarantee that it's the opposite direction of our velocity. But that's a little bit clunky. Absolute values are kind of annoying to work with. So let's just see what can happen here. So if we combine gravity and drag in one scenario, and we do this slow, and slow, by the way, means like very slow, like a ball moving in honey. Think of how quickly that is. Or dust particles moving in air. If it's ever been a very sunny summer day and you have the blinds open, then you might be able to see the dust in the room moving. It's not moving very quickly. And then fast would be more like a ball in water or air. Okay, so let's just do the slow scenario. We could do the fast too, but it would be different. Okay, so we have force, which is, these guys are dependent on velocity, so we'll use this velocity version of force. So force, which is m times the derivative of velocity, equals, we have gravity, negative mg, and then we have drag, and we're doing slow drag, so negative gamma v. And then once we figured out what gamma was, we might be able to divide through by m. So let's do an example of what the numbers would be. You could have this differential equation, dv by dt equals, the m's would cancel out here, so you just get negative g. We're going to use the crudest approximation. We're going to use 10. So this would be negative 10 minus, and then whatever gamma over m works out to. So we can have any number times v. In our example, we're going to do negative v over 5. And then we could do a similar example for fast. So the only change in fast is that instead of gamma v, we have gamma v squared. So we could have dv by dt is -10, and then this could be a plus or minus, and we have v squared over 5. So in both of these cases, gamma over m is 1/5. We don't know what gamma is.